Well, good afternoon. Welcome to NASA headquarters in Washington, D.C. My name is Dwayne Brown with the Office of Communications. On July 4th, we celebrate our nation's independence. And also on that day, NASA looks to accomplish yet another historic achievement in our solar system and beyond. To set the stage for what you will hear today, please welcome to the podium the Acting Associate Administrator for NASA's Science Mission Directorate, Jeff Yoder.
It really is an exciting day today. The NASA Science Mission Directorate's mission is to innovate, explore, discover, and inspire. And with over 100 missions, it's really easy to use this entire portfolio in many ways to accomplish this, not only for the science community, but also for the world and for humankind. Last July, we saw the first ever up-close images of Pluto, the distant Pluto. This July 4th, we will not only celebrate the nation's Independence Day, but the science community will also prepare to begin writing new chapters in our science book about Jupiter and perhaps about ourselves. In fact, NASA science is really interconnected. So Earth science, heliophysics, astrophysics, and of course planetary science were all part of developing information needed to develop this journey, this mission. And of course, we will, as we complete this mission, as we go forward, achieve and learn more about ourselves and about the environment. As we near the doorstep of Jupiter, NASA is also preparing to launch this September a spacecraft to a large asteroid. In addition to upcoming launches to further study the Earth, the Sun, and our universe as we've never done before. NASA's science is the greatest engine of the scientific discovery on the planet, and today you will hear more about the engine's vital mechanisms. And then last is you look up in the sky and watch the fireworks July 4th. Think about NASA as we're above and beyond with our missions. With that, Dwayne, we turn it over.
All right, let's see. Before I introduce our panelists, all the information you will hear today and much, much more available on the internet at www.nasa.gov/Juno and also missionjuno.swri.edu. Now, if you go to those websites, and I would encourage everyone, particularly the folks not just here but watching this program, there is an incredible video that really gives you the drama and the intensity of what this incredible team is going to experience. So I encourage you to look at the video. Social media. The excitement is building. Join the conversation. Facebook, Twitter, YouTube. There are a lot of folks talking about the countdown to Jupiter. And send in your questions at #AskNASA. You're going to hear a lot of information. We're going to try to get to many questions, and if we can't get to them today, we'll have the science team respond to your questions as soon as possible. So, before we get started, let me introduce you to today's presenters. First up, Diane Brown, Juno Mission Program Executive, NASA Headquarters. Scott Bolton, Juno Principal Investigator, Southwest Research Institute, San Antonio. Rick Nybakken, Juno Project Manager, Jet Propulsion Laboratory, Pasadena, California. Heidi Becker, Radiation Monitoring Investigation Lead, also from JPL. Alberto Adriani, Juno Co-Investigator from the Institute of Space, Astrophysics, and Planetology in Rome, Italy. And also, I want to recognize two individuals in our front row who will be participating in the question and answer period. And first, a gentleman that doesn't really need a lot of introducing. He's done a lot of press conferences, and he keeps the Office of Communications very busy with the incredible planetary missions. Jim Green, the director with Planetary Science Division at NASA headquarters. And also joining us, Enrico Flamini, chief scientist for the Italian Space Agency. And with that, from one Brown to another, over to you, Diane.
Thank you, Brian. Good afternoon. We are so excited to be within 3 weeks of our return to Jupiter, our largest and one of the most fascinating planets in our solar system. We have been to Jupiter before, but we still have questions, and Juno is poised to begin answering them. Other missions to Jupiter included Pioneer 10 and 11, which flew by the planet early in the 1970s, and Voyagers 1 and 2, which flew by in 1979. Other missions have also gone by Jupiter on their way to other destinations, but the most recent mission there was Galileo, which in 1995 dropped a probe into the Jupiter atmosphere. Most of what we know today about Jupiter's complex system of moons, rings, and the magnetic field come from the Galileo mission. Juno is the second of 3 missions within the New Frontiers program in the Planetary Science Division. As Jeff mentioned, you all will remember New Horizons, which provided those amazing images of Pluto last year. And then this September, OSIRIS-REx will be launching to return samples from the near-Earth asteroid Bennu. Juno was selected out of the second New Frontiers announcement of opportunity in 2005, and it launched in 2011. It has a life cycle cost of $1.1 billion. The Juno team has representation from around the world. The science and spacecraft management teams are distributed across California, Alabama, Texas, Colorado, and here in DC. The scientists come from across the country and many of the states within the United States. And the science instruments were developed in Maryland, Texas, Iowa, California, Denmark, and Italy, with contributions from many other places. NASA has a long history of significant milestones on the 4th of July. Just to name a few, in 1997, the Mars Pathfinder landed on Mars and spent the next month providing amazing images of the Martian landscape. In 2006, the Deep Impact mission collided with the comet Tempel 1 to learn more about what comets are made of. And of course, this year we have our own 4th of July fireworks excitement as we arrive at Jupiter, and we hope you all come along for the ride. And with that, I'll hand it off to Scott to tell us more about the mission and the science.
Thank you, Diane. So I'm really excited to be here. We're just a couple of weeks from arriving at Jupiter, and it's been such a great journey, and I can't wait to get there. So one of the primary goals of Juno is to learn the recipe for solar systems. How do you make the solar system? How do you make the planets in our solar system? And in fact, not just our solar system, but how do you make the planets that we discover in other solar systems? We're seeing planets around other stars now. And what we really want is the recipe. How do you make these planets? Now, Jupiter holds a very unique position in helping us learn about that recipe because it was the first planet to form. So it gives you that very first step in the recipe. What happened after the sun formed that allowed the planets to form? Because that's really the history of not only our system, but us here at Earth. And we don't currently understand how we formed Jupiter. We're puzzled. We learned some things from previous missions, but Jupiter looks a lot like the sun, a smaller version. It's almost all hydrogen and helium, just like the sun is. In fact, the whole universe is almost all hydrogen and helium. But when we look closely at the composition of Jupiter, we learn that it has an enrichment of what scientists call heavy elements, all the elements beyond helium in mass. So the carbon, the nitrogen, the sulfur, the noble gases. Jupiter's enriched with these elements compared to the sun. We don't know exactly how that happened, but we know it's really important. And the reason it's important is the stuff that Jupiter has more of is what we're all made out of. It's what the Earth is made out of. It's what life comes from. And so learning about that history is really critical if we're going to figure out how we got here and learn about the Earth and how we find other systems like the Earth elsewhere. So can I have the first animation? So here you see a scientist and artist concept of the early solar system. First forming, you have the young star, our sun, and you have clouds of gas and dust surrounding it. These are the leftovers. The sun forms from a cloud like that. It collapses on itself, and then there's leftovers. Not much. Sun sucks up most of them. Jupiter sucks up the majority of Jupiter sucks up the majority of the leftovers after the sun is formed. If you take all of the rest of the solar system, all the planets, all the asteroids, comets, they all fit inside Jupiter. So it forms first, and it uses up most of the leftovers. We are the leftovers of the leftovers. Something happened between the time the sun formed and the time Jupiter formed that allowed it to be enriched in these heavy elements that eventually leads to us. We don't know what happened there, but it was very important because the beginning of the process of how you create the terrestrial planets and life started already early in the solar system when we saw Jupiter form. It started to get this enrichment, and the rest of the planets got even more, right? The Earth is almost all of these heavy elements. And so the way Juno investigates this is by looking into the interior of Jupiter, seeing how is it built, what is it made out of. These are the clues for us to compare to the sun and understand the processes that went on in the early solar system. Can I have my next video, please? So here you see Jupiter spinning around and these beautiful zones and belts. What's underneath those? So we have special instrumentation that looks deep in at the magnetic and gravity field to see how it's spinning inside, how is it structured? Is there a core in the center of Jupiter? If there is a core of heavy elements, a bunch of rocky, icy materials squeezed down in the center of Jupiter, it tells us something about the early process in the solar system, because that means that the rocks must have formed in the early solar system before Jupiter did. Essentially, Jupiter got built around those rocks. We don't really know if there's a core in the middle of Jupiter. That's one of the things that Juno is going to investigate. If there is, then that means it tells you sort of when and how and a little bit of where Jupiter must have formed. That tied with the water abundance are two key discriminators on theories of how and where Jupiter formed. The other investigation that Juno does is we go right over the poles. So in order to do all of our science, we're a polar orbit. We're the first spacecraft to go over the poles of Jupiter. And we go very close. And as we fly over the poles, we're flying right over Jupiter's intense aurora. Its northern and southern lights. Can I have the next video? These are the strongest auroral emissions in the entire solar system. Jupiter is a planet on steroids. Everything about it is extreme. Those aurora are incredibly powerful compared to even the Earth's. These lines you see, that you saw around there, those are magnetic field lines. The auroral particles are coming down. Juno is flying right over those with a suite of instruments to investigate those aurora and the polar magnetosphere for the first time and compare that science and what we learn with how the aurora work on Saturn and the Earth. And from that, we start to learn how planetary aurora work in general. So what's the tool that we use to learn all this? It's the Juno spacecraft. Can I get the next animation? So here you see Juno. This is an incredibly large spacecraft. It's solar powered. Each one of those solar arrays is 8.5 meters long apiece, like 25 feet. This spacecraft is the size of a basketball court. It's enormous. The scientific instruments are stationed in between the solar arrays. As Juno cartwheels through space, it spins twice a minute. Each of the science instruments takes its turn looking at Jupiter as we spin. There's not a lot of fancy pointing needed with this spacecraft. It's all built into the design. We're spinning over Jupiter, cartwheeling, and all the instruments look down and up, taking their turn, looking at Jupiter, and then looking away to calibrate. So it's a very efficient design, and even with those giant solar arrays, Jupiter is about 5 times the distance from the sun that the Earth is, so the sunlight is only 1/25. So even with enormous solar arrays that are very efficient, we're still only getting a few hundred watts, a couple of light bulbs. And so the spacecraft is designed to be extremely efficient. Okay, I'd like to turn it over to Rick Nybach, our project manager, and he'll tell you more about the development of Juno and the schedule for the events that are coming up.
Thank you, Scott. Scott and the science team asked us to take a spacecraft where no spacecraft was ever gone before, deep into the harshest radiation environment, the most treacherous environment in the solar system aside from the sun, and operating farther from the sun than any other solar-powered mission in history. So let me talk about some of the features on the spacecraft that enable us to meet those challenges. The first thing you notice when you look at the spacecraft is the immense size of it. As Scott said, it's roughly the size of an NBA basketball court. But these massive arrays contain 18,700 solar cells and can generate almost 14,000 watts of power near Earth. That's more than our spacecraft is designed to handle. So when we flew by the Earth, we actually turned off most of the solar arrays. We only had 2 of the inner panels on. But at Jupiter, where the sunlight is only 1/25th of what you receive at Earth, these massive arrays still generate 530 watts of power. As Scott said, that's a very power efficient spacecraft, only requiring the equivalent of 5 floor lamps in your living room. To meet the radiation challenge, cue the vault, or cue the video there, we designed a vault, a radiation vault that protects our most important electronics. They're housed, as you walk in here along the solar array, you can see that square rectangular box underneath the high-gain antenna. That's the radiation vault, and that's where all our electronics are housed, except for the instrument sensors, which, as Scott said, are spread around the periphery of the spacecraft. So let's talk a little bit about what we've been doing the last 5 years. Cue the video, please. We launched back in August of 2011 from Cape Canaveral Air Force Station on an Atlas 551 launch vehicle. This took us out past Mars orbit, where we fired the main engine twice back in 2012. This increased our speed as we went back around the sun and flew by the Earth, receiving a gravity assist that increased our velocity by 70% of what we got from the launch vehicle back in 2011. This gave us enough energy finally to reach all the way out to Jupiter, and we'll arrive there and fire our main engine to go into orbit around Jupiter on July 4th. May I have the slide, please? Here's what's ahead of us in terms of configuring the system and doing the last series of activities to be ready to fire our main engine. We open the main engine cover, we pressurize the prop system. There's some other preparational steps there before we start the JOI sequence 5 days before we arrive. The last 5 events there, all on July 4th, all happen within hours of the main engine burn. So we start tones, which is a special communications mode that we use when we're in our burn orientation. Our normal communication antennas are no longer pointed at Earth, and so we use a special communications method to signify the various milestones throughout the sequence, leading up to the burn, signaling the start and the end of the burn, and also after the burn. You've probably noticed sometimes listening to your car radio, you'll hear an emergency broadcast system test, and they'll just send a tone out. That's what the spacecraft does, and it sends different frequency tones to mark different events. Then, as we move closer to the burn, we move through turn to the burn attitude. We're now oriented 90 degrees away from the sun with the engine pointed in just the right direction to slow us down enough to be captured into Jupiter's immense orbit. Next video, please. Can you cue the next video? Then we start our main engine burn. This is our 3rd main engine burn. The 4th one will come 107 days later. The first one here is 35 minutes long. The 4th main engine burn on August 27th will be 22 minutes long, and that will get us into a 14-day science orbit. So it's really a well-designed mission when you think about it, because We fired our main engine twice already, which really gave us an excellent level of preparation for this very important event, firing the main engine the third time. We know how to set up the propulsion system. We know how the engine performs. The only thing new here is how the main engine performs and the spacecraft performs in Jupiter's intense radiation environment. And Heidi's going to tell us a little bit more about that intense radiation environment.
Thank you, Rick. Jupiter has the scariest radiation environment of any planet in the solar system. It's the harshest, it's the most intense, and it hasn't been fully explored yet. And it hasn't been fully explored where we're going. Jupiter's magnetic field has trapped a huge population of electrons and accelerated them to the point where they're moving at almost the speed of light. They're incredibly penetrating, they're damaging to electronics, and they can create enough noise in a detector to totally blind a camera. First animation, please. Jupiter's electrons are moving so fast, they're spiraling up and down the magnetic field lines and bouncing between magnetic mirror points in a few seconds. And once the electrons hit a spacecraft, they immediately begin to ricochet and release energy, creating secondary photons and particles, which then ricochet. It's like a spray of radiation bullets. Juno's protected from the radiation a little bit by our polar orbit. But if we'll cue the next animation, as the mission progresses, Juno's orbit will descend further and further into the harshest equatorial region of the radiation belts. And every science pass, Juno has to fly through very intense high-latitude regions close to the planet, twice. If we did nothing else, Juno would be experiencing a radiation dose of over 20 million rads, which is like a human undergoing over 100 million dental x-rays in a little over a year. So Juno's wearing a suit of armor to face Jupiter and bring down the dose. Next animation, please. Here again is our radiation vault. It's made of titanium, and the walls are about 1/2 an inch thick. The vault weighs almost 400 pounds empty, and it's enough to bring down the radiation dose by a factor of 800. Outside the vault, all of the instruments are also wearing bulletproof vests. And in fact, the camera head of our star tracker is the most heavily shielded thing on Juno. This black box you see in the animation is holding our star tracker. Without that extra protection, we wouldn't be able to navigate Juno. A star tracker is a lot like what sailors used to do on ships in the old days. They would look into the sky and look at the patterns of the stars to understand where they were pointing to navigate the sea. And a star tracker does pretty much the same thing, only it does it by taking pictures of stars. Juno's star tracker is 4 times heavier than the most heavy standard star tracker, because without the protection, the noise from the penetrating radiation would be too high to see stars, and Juno would never know where it was pointing. Next animation, please. This is an animation of Juno's trajectory on August 27th. It's our closest approach to the planet. That'll be 2,600 miles from the cloud tops. And that orange and yellow map is our model of the radiation. We graze through it twice. But this is a region where no spacecraft has ever been. And this is just a model. There isn't a dedicated detector on Juno to sense the high-energy electrons at Jupiter, but we have a way to watch and learn. Next animation, please. We'll be looking at the noise in our cameras and counting the hits of the radiation that does get into our pictures. This is a simulation of what our radiation models predict our star tracker star images will look like as we fly through those very nasty regions close to the planet. And now to tell you a little bit more about one of Juno's science instruments, I'll hand it over to Alberto.
Thank you, Heidi. Now I'm speaking about JIRAM. The acronym stands for Jovian infrared auroral mapper. The instrument has a small telescope and 2 detectors, so that it's practically a double instrument. It's a camera and a spectrometer at the same time. GIRAM will observe the planet in infrared light. GIRAM is an Italian space agency instrument, and Italy has a long history about building similar instruments for other missions. I can remind here a couple of NASA missions like Cassini and Dawn. GIRAM was primarily conceived to give a contribution to the study of the magnetic aurora, the magnetosphere of the planet and the interaction of the magnetosphere with the planet itself. In particular, to study the aurora. Can I have the first picture, please? In this picture, you can see 2 auroras. On the left, there is an ultraviolet aurora that has been measured from the space, from the Hubble Space Telescope. On the right, there is an infrared aurora, measured from ground in the infrared, from an observatory on ground. So there are 2 auroras, because actually we have 2 different emissions from the aurora, because different emission because the causes of this emission, light emission, is different. What causes the emission of the auroral emission is these electronic, very energetic electrons that fall to the planet, and they interact with the hydrogen, giving the ultraviolet aurora, or its ion H3+, giving the infrared aurora. And GIRAM will look at the infrared aurora. So, in the picture I showed before, it's actually the only case from the previous measurement we have on the Jupiter aurora in which the two phenomena have been measured contemporarily. On Juno, we are going to have many occasions to have simultaneous measurements of these 2 aspects of the Jupiter aurora. Can I have the next picture? GIRAM will also be used to study some characteristics of the Jupiter atmosphere. In particular, on Jupiter, there are some areas, you see in this animation the brightest spot here, where the atmosphere is almost clean without big clouds, and GIRAM can look deeper inside the atmosphere and from those holes, in those holes, measure some concentration of some compounds that have significant role in the atmospheric chemistry of the planet, cloud formation. Other goals are study of the Jupiter cloudiness and, in some extent, dynamics of the atmosphere. Can I have the next animation, please? GIRAM, in this animation, you see the instrument, the optical head of the instrument, which is mounted on the backside of the spacecraft, the aft deck, which is the face of the spacecraft, which is always looking at the deep space. You see the spinning of the spacecraft, and the colors you have seen before, they are the two light you see reaching the instrument is actually the path of the light coming from the space, from the planet, reaching the instrument. GIRAM has the spinning mirror to compensate the movement of the spinning spacecraft. In this case, this is needed because during the observation, the image or the target we are going to observe has to be still. The next movie, please. In this movie, I show a simulation of how the instrument can look at the planet. You see here the moving part is the track of the detectors of the instrument. The two rectangles are the two areas of the imager dedicated to the aurora measurements and the thermal emission measurements. Finally, you can see here the pink oval, which is the main structure of the Jupiter aurora, and the red curve that depicts the track of the satellite Io to the contribution to the auroral pattern. So we are looking forward to get to the Jupiter in a couple of weeks. We are very excited about. And so let me give the microphone to Scott to give us the conclusion.
Thank you, Alberto. So the Juno team is really excited. All the scientists and engineers that made Juno happen are just so excited that we're finally arriving at Jupiter, and we're going to start this incredible journey of learning our history and what's inside Jupiter and all about how the physics works at Jupiter. And we want the public to be able to share in that excitement. We want them to join and jump on and ride with us into our journey of exploration. And so I'm going to tell you about a couple of items that we have with Juno that help enable that. One of them is our visible camera. It's a color camera. We call it Juno Cam. Juno Cam will provide the very first views of Jupiter's poles. We don't know what they look like. And we're going to fly over those and see them for the very first time. It'll also show the most incredible close-up views of Jupiter ever seen, because we are coming so close to Jupiter. The public can join us on that camera because it's really a public camera. That camera is on board, and we have a website set up where the public can sign on and help vote and decide where JunoCam points. What do we take pictures of? What features on Jupiter are the most interesting? They can engage in the debate of which things are most important to photograph. And then when the data comes down, they can produce the first images of Jupiter and post them on our website. And so this camera is really allowing the public to join in and become part of the Juno team, doing some of the science, creating some of those images, and sharing those with the world. And we have another aspect. I often get asked, do we have any passengers on board? Well, we do. We have 3 special passengers. They're actually Lego minifigures. These are made by the Lego company in a special agreement with NASA, and they're made out of spacecraft-grade aluminum. And we have 3 of them. This is Juno, the goddess. She is the sister and wife of Jupiter, who's right here holding his lightning bolt, and Galileo, in honor of his great discoveries that enabled us to learn so much about the universe and nature. And he's holding Jupiter and his telescope. And we put these Lego minifigures on Juno in order to inspire and motivate and engage children, to have them help them share in the excitement of space exploration and reaching for the best goals that you can. Reach out, literally, for the stars. We want to teach them that they can accomplish anything. And we're reaching for the stars here. They can join us, or they can reach for their own stars. We want to just inspire them and get them excited about the whole space exploration program and learning about nature. And so July 4th is coming up, and we're about to arrive. And I really look forward to that, and I hope you'll all join us as we arrive at Jupiter and jump on the Jupiter train. Thank you.
And thank you all. A reminder for the folks who are here in the auditorium, you may have noticed that there is a Lego-made spacecraft out in front of the auditorium, and you actually can see where those little guys are on there if you look very closely. And for our folks watching, we'll see if we can get a picture and put it out on social media on the web so you can actually see that. Very, very cool. We're going to take some questions, and I think Diane and Scott, one of the first questions we're going to get is, where can they get some of those cool team shirts you guys have on? Very awesome shirts. We're going to go to the phone line first, and we're going to have Mike Wall from space.com.
Thanks, guys. This is probably for Scott. Scott, like you were talking about how if you do find out Jupiter has a core, that would tell you a lot more about where it formed, how it formed, et cetera. I'd just like to know, could you go into a little more detail about what you mean and what you could conceivably learn just from the core and like sort of why that would teach you what you would hope to learn? Thank you.
Sure. So Jupiter is a giant ball of gas. It's most of its composition is just like the sun. It's almost all hydrogen and helium. It's enriched in these heavy elements. We don't understand exactly how that happened, but we also don't know if there's a core in the center of Jupiter. We don't know if it's just gas compressed all the way down, basically, and just there's no core of rocky material in the middle, or if whether there's a core. So we don't know that because we don't have very precise data on the gravity field of Jupiter up till now. We know that Saturn has one of these cores. We don't know about Jupiter. And the real question is that if Jupiter has a core of rocky material, and we'll be able to learn something about that by studying the distribution of mass inside of Jupiter through the gravity field, then that core should most likely will have formed in the early solar system, and then Jupiter kind of forms around that core. Because once you form Jupiter, you have an incredible giant atmosphere. And so if rocky material, such as asteroids or something, were to come in and hit Jupiter now, or after it forms, they will evaporate basically in the atmosphere. They'll burn up, and they won't ever reach down to build a core. So when we measure it, if we see that there's a concentration of heavy elements or a concentration of mass that's very significant in the center, that implies that Jupiter formed after rocks started to form and ices started to form in the early solar system. Alternatively, Jupiter may have formed like we think the sun did, which is just a collapse of the gas and dust, and you don't need any rocky material in the center.
Next question is from Bill Harwood, CBS News. Bill? Bill? Okay, let's go to Alex Whitsey from Nature.
Yes, hi. My question is for Scott. So Juno Cam should have been taking pictures already. When do we get to see those first pictures from Juno Cam?
So we've been taking a few test images of Jupiter. It's very small in the fields of view, but we will release it's already been released, some images that we took of Earth. But the first time we will release images of Jupiter when we get closer is on July 4th.
Okay, we're going to take some questions from social media, but sir, you have your hand up. Please identify yourself. And
Thank you. Eddie Gonzalez, Jet Propulsion Laboratory. Once the spacecraft arrives to Jupiter on July 4th, how long will it take a signal from the spacecraft to arrive?
The one-way light time is 48 minutes. So the burn actually occurs at a time that after we go through the one-way light time, we'll start receiving the burn telemetry starting at 8:18 Pacific, and the burn would nominally end Earth receive time Pacific again at 8:53 p.m.
okay, there's a lot of buzz on social media. I'm going to turn it over to Emily Fafaro. What's the public excited about?
Sure, yeah, they have a lot of questions. The first one comes from Marielle, and she asks, what are the potential mishaps or problems that could occur from the point of insertion to Juno's 20-month journey?
Well, one of the things, of course, we spend a lot of time thinking about is radiation effects. And we've thought about this. I've been working on the project since 2006, and I can tell you we've thought about it almost every day. But we built up from the radiation models. We've done extra parts testing. We've put additional shielding on the spacecraft. And we put a lot of thought into how to respond, even though it may be unlikely, how to respond to any surprises we may get from the radiation environment. So we have a 14-day science orbit, and one of the things we do for the magnetometer investigation, for instance, is we put a special feature on board that if we were to have a computer hiccup when we did closest approach to the planet and we temporarily lost data from all the instruments, this would automatically turn that one instrument back on, because the magnetometer map, the magnetic map of 32 orbits, is the one that's the most challenging for us to achieve. So there's a number of measures like that we've taken to respond to the challenges ahead of us.
Let's take 2 more from social media, and then we'll go back to the phone lines. Good.
Great. This one's from Xavier, and he says, will there be amazing pictures, and will we get to know more about what's under those cloud layers?
Yes, I expect we will have amazing pictures. Just to see the first glimpse of what the poles look like will be amazing by itself. But we will get incredible pictures close up, and we'll get them in not just visible light, but ultraviolet and infrared. And we have special instrumentation called a microwave radiometer that actually can see beneath the cloud tops. So we've never really seen how deep the zones and belts or the Great Red Spot really go. We don't know those routes. Presumably the routes to a Great Red Spot must be fairly deep, because it's a storm that's lasted for hundreds of years. And so we have instrumentation for the first time that's actually going to see beneath those cloud tops, and we will be able to make images. They're not exactly like you would normally take with your phone cameras, but we will see what it looks like underneath those clouds and how deep those zones and belts go. So we'll get some great stuff.
Okay. And this question is from Andre, and he says, will Jupiter's moons be studied by Juno?
Jupiter's moons will be studied a little bit by Jupiter. It's not our focus. Our focus is, of course, the planet itself. But we are orbiting nearby there, and I mean, the moons are nearby, and we don't go very, very close to them. So we're not going to get close-ups of the moons, but we will get some distant shots, and they will be unique because we'll be coming from above and below, and the moons have never been seen from that direction.
Okay, let's go back to our phone lines, and then Emily, I'll probably come back for some final questions. But Tracy Watson, USA Today. Tracy.
Thanks, Dwayne. Just wanted to ask what the kind of nail-biting moment is going to be during the orbit insertion. When should all of us be watching, and when are you going to be kind of scrutinizing the numbers most carefully? Thanks.
Well, I think the part that we're all going to be watching most intensely, of course, is the main engine burn itself. And I can tell you when that completes, you're going to see a lot of celebration, because that means we'll be in orbit around Jupiter. And that'll be really cool. So, oh, well, that's July 4th. And as I said earlier, the main engine burn Pacific time is 8:18 to 8:53 p.m.
Okay, I believe we have Bill Harwood back. Bill Harwood, CBS News. Bill?
Yeah, thanks. One quick one, I guess, for Rick again. And it's related to Tracy's question. What sort of margin do you guys have on the JOI burn? In other words, what's the desired burn time in delta V, and what is the minimum delta V you need to achieve any sort of useful orbit? And I guess related to that, I'm wondering that if you don't burn at all for whatever reason, where does the trajectory take you, and would there ever be a chance to recover? Thanks.
There's a lot of questions buried in there. Well, let's start with the burn time. First of all, a 35-minute burn gets us into a 53-day orbit. The minimum amount of burn that we need to get into orbit at all, which is a rather large orbit, is on the order of 20 minutes. But we put enough safeguards in the system, including what we call auto restart. So the system is designed if, for instance, the radiation causes the computer to reset and the engine stops. It's not designed to just protect the spacecraft. It's designed for this one portion of the mission to restart the burn. So it'll do a quick recycle and within 500 seconds restart the burn. So most likely we expect to get all the way to 35 minutes, but if we don't get all the way in one shot, we'll get there eventually. I can tell you that our previous science or capture orbit was 100 minutes, which is about a 30-minute burn. So even getting to a 30-minute burn without interruption gets us into a fabulous science orbit. We've never been to this region of the planet, so even a few orbits gives us tremendous science resource. But of course, we want the whole enchilada. And there was a second part of the question, if you could refresh my memory. Oh, if we don't burn it all, where do we end up? We don't end up in a very exciting spot. We come in, yeah, we're in orbit around the sun. We'll get a nice deflection. We're above the ecliptic and above the planet, and we'll be tilted down, and we haven't studied that too much in terms of where we end up because we focused on success and not failure. But it is an interesting question.
It's a one-shot deal. I mean, the whole thing's riding on this JOI, Jupiter Orbit Insertion activity on July 4th. So, you know, somebody asked, when does the nail biting start? It's already started. I'm getting close. I'm you know, a mix of excitement and anticipation with tension and anxiety. And I felt the exact same thing on the day of the launch, which was probably our highest risk in the entire mission. I think the Jupiter orbit insertion is the second highest risk. Everything's riding on it. This spacecraft is very complex. This was a great challenge. We are going literally where no one has gone before. It's the greatest challenge in some ways because Jupiter is the most extreme planet we have. And we're going right next to it, right into its guarded areas, right? It's a planet on steroids. Every single thing about it is the most extreme. It has the strongest magnetic field. It's whipping around, spinning the fastest. It has the most intense radiation. We're moving faster than any spacecraft. In fact, any human object has ever gone. So everything about it, we've got to do the extreme. It's got to do the extreme, but we've taken every human ingenuity idea and put it into this, right? And we put together an armored tank going to Jupiter. So we're shielded and ready, but there's definitely risk.
And let me remind our studio folks here and watching us that if you go to the website, nasa.gov/Juno, Jupiter Into the Unknown is a 2-minute video that you will truly see with this team. We talk about nail biting and the unknown and the drama. When we conclude here, get to your computer, get to the internet, journey into the unknown. It will really give you a full flavor of what this team is in store for, or what they don't know what they're in store for. We're going to take one more call, and then we're going to come back for 2 more social media questions and wrap up. So back on the phone, Joe Palca from National Public Radio. Joe.
Hi, guys. 2 questions, actually. One, can you tell me a little bit more about the provenance of Juno Cam? I seem to recall hearing it was originally slated for a Mars lander mission, and then it got repurposed. And the other question has to do with the star tracker camera that Heidi was talking about earlier. There are 4 other star trackers on the magnetometer arm that are just for pointing purposes, but they're not involved in navigation. So those were the 2 questions.
So I'll take the Juno Cam and the magnetic star cameras for you, and then we'll let Heidi take care of the main star tracker. So Juno Cam is a copy, a close copy, but not an exact copy, of other cameras that have been flown to Mars, built by a company, Malin Space Sciences. And when we went to them, we went to get something that we could use for the public and get great images. I couldn't imagine that we were going to go all this way and not see what Jupiter's poles look like. And they agreed to make basically a copy of something that was on Mars. So it wasn't taken and repurposed. It was specifically designed and built for our mission. But its basic design was taken from Mars missions. But it did have to be customized. We have a very extreme radiation environment. We're also spinning, so it works a little bit different than the Mars cameras. The second part of the question that I'll take was the 4 star cameras that are tied to the magnetometer investigation. That's the end of one of our solar arrays. You'll see that one of them looks a little different on the end than the rest. That's because that's an optical bench where we house the magnetic field investigation. There are two sensors that measure the magnetic field. That magnetic field measurement is a little bit like what you get at the airport when TSA checks to see if you've got any metal on you. They basically have more basic magnetometers, but they're looking to see if the magnetic field gets distorted, and then they know you have some metal in your pocket. Ours are a little bit more precise. They're, in fact, the most precise magnetometers ever designed. And they're at the edge of one of these long solar arrays. The reason we have 4 star trackers out there is because we want to locate exactly where those magnetometers are when they make their measurement, because they're mapping very, very precisely, more precise than any previous spacecraft was ever done, the magnetic field of Jupiter. And we want to know exactly which way the vectors are pointing in this invisible force field, so that, because it tells us something about the interior structure of Jupiter and how the magnetic fields are formed. And so those cameras are there to detect any slight movement in those solar arrays. If they were to bend or get deflected in any way, they will locate exactly where those magnetometers are being measured compared to the main body of the spacecraft. And those star cameras or star trackers are called advanced stellar compasses. They're built in Denmark by Danish Technical University, and they are very special cameras because they're magnetically clean. In other words, they don't interfere with the measurement of the magnetometer. So some cameras give off their own little magnetic field, and so we had to be very careful to get ones that were what we call magnetically clean. Now I'll turn it over to Heidi to answer the other part of the question.
Okay. And the star tracker that I was talking about was the Spacecraft Stellar Reference Unit, and that's the star tracker that supports attitude determination for Juno. And it was made by a company called Celix Galileo in Florence, Italy. So that's our other Italian instrument on Juno.
Okay, Emily, we're going to take 2 more, and then we'll wrap up.
It's from Jay, and he asks, why will Juno deorbit in 2018 after less than 2 years of orbiting Jupiter? What limits the length of the mission?
Oh, go ahead. One of NASA's investigation or future missions that they want to undertake is a mission to one of Jupiter's moons, Europa, and they suspect there may be life underneath the ocean. Well, the last thing you want to have happen is to get there and find out it's been contaminated by organisms from Earth. And so they have a program called planetary protection. And one of the requirements we have is to have a very low likelihood that we'll ever hit Europa and contaminate it. And so we designed a mission that after we complete our 32 science orbits, we'll go out to Apogee, the farthest point of our orbit, and take some energy out of the orbit, and the next time we won't make it around and we'll go into Jupiter. Destroying the spacecraft that way is the way that we help ensure we'll never hit Europa in the future.
All right, this question is from Melissa, and she asks, how does a better understanding of Jupiter unravel the origins of Earth or our solar system?
Well, we don't know exactly how Jupiter was made, and we don't understand how it's enriched in these elements of carbon, nitrogen, sulfur, and we don't actually know how much oxygen or water is in Jupiter. At the same time, we don't understand how Earth got its water. We have some theories. Some people thought it was comets, but the comets that we've measured don't fit. It may not have been comets. Maybe it was asteroids. Maybe the thing that supplied the water isn't out there anymore. But when you go to study Jupiter and learn about how it formed, what you're really learning about is the history of those volatiles, those elements that eventually made us. We're learning about what state and how they might have been distributed early in the solar system, which will fold into models of how you not only make Jupiter, but how you eventually make the other planets.
Okay, that's going to do it. I want to remind the many folks watching us that there's yet another reason to save the date on July 4th. It is going to be incredible. Come and join the ride. Go to the website for more information and updates at nasa.gov/Juno and missionjuno.swery.edu. The countdown to Jupiter has officially begun. Join us. We'll see you out in California July 4th. Thank you.